scratch the surface of learning to undo what we've done all semester. That's how it is in every math class you've ever taken. You learn to do something and then you learn to undo it. You learn to add and then you learn to unadd, and you called it what? Subtract. You learn to multiply and then you learn to unmultiply, and you called it divide. You learn to, oh, this is a good one. You learn to exponentiate and then you learn to unexponentiate. What do you call that? Taking logarithms. Good. Well, in calculus, we spend the first 13 weeks of the semester learning how to differentiate, and the last 1 week learning how to undifferentiate, or we're going to call it anti-differentiate. Anti-differentiation or integration. Those are two words that pretty much mean the same thing, and that's what chapter 5 is about. We're only going to do 5:1 through 4. We will just barely touch 5:2 and 5:3 Friday, 5:4 Monday, review for test 4 Wednesday, and then test 4 is next Friday. So that's how close we are to the end. But before we look in the book, yes?
Is this hard?
Yes, this is the hardest thing we've ever done. It's going to make you cry. I hope you brought your Kleenex.
Are you being serious?
No, I'm not being serious.
No.
If I was going to make you cry, I wouldn't warn you. I would let it sneak up on you. All right.
Is that hard?
Before we look in the book, I want y'all to squint really hard and try to answer this question for me. What function, it's like playing Jeopardy. I've been asking the questions, you've been giving the answer. Now I'm going to give the answer, and you have to tell me what the question is. So I'm going to give you a derivative, 3x squared. I want you to tell me the function that if you took its derivative, you would get 3x squared. X cubed. Everybody just know God spoke to everyone at the same time. That's cool. Now, x cubed is an antiderivative of 3x squared, but I didn't mean to use the word the antiderivative of 3x squared, because there are other functions whose derivative would be 3x squared. Can you think of another one?
3x squared plus any number.
X cubed.
Subtracted any number.
Or not 3x squared, but x cubed.
X cubed.
X
Sorry.
cubed, how about x cubed plus 7?
Yep.
That derivative would still be 3x squared. What about x cubed minus e? Not even the x, just the number e.
Yeah.
The derivative would still be 3x squared. So what we just discovered is that this function doesn't just have one antiderivative, it has a whole family of antiderivatives. Actually, we could write the antiderivative as x cubed plus any constant, and that would be the whole family of antiderivatives. So if capital F prime of x gives you some little f of x, then capital F of x is called an antiderivative of little f of x. Now, I have to read that several times, but it's actually the next sentence that makes sense to me. In other words, capital F of x is an antiderivative of little f of x, means that capital F of x is a function whose derivative gives you little f of x. So I'm going to give you some little f of x. You're going to find capital F of x whose derivative is that little f of x. Honestly, I wish they'd use some different letters other than little f and capital F, but that's not the way it's written in the book. I wanted to write this the same way that it's written in the book. If this 3x squared is my little f of x, then all of these guys are my antiderivatives of that little f of x, because they're the functions whose derivative is this little f of x. All right, a little bit more terminology, and then we're going to look at some things in the book. The family of all antiderivatives of the function little f is indicated by this new symbol. This new symbol is called the integral symbol, or the integral sign. When we write an integral sign in front of f of x dx, that means the whole family of antiderivatives of little f of x. F of x is called the integrand, and dx indicates the variable of integration. It's what you're integrating with respect to. That notation, that integral sign, f of x dx, is called the indefinite integral of little f of x, where that's the integral sign. This is the integrand, just like what you're taking the square root of is the radicand. What you're integrating is called the integrand. Dx is your variable of integration, which is not going to be terribly important to us when we're dealing with functions that only have one independent variable. But in Calculus 2, when you're integrating functions that have more than one variable in them, you're going to have to say whether you're integrating with respect to x or integrating with respect to y or whatever variable you have. F of x, capital F of x plus c is called the it's called the whole family of antiderivatives of little f of x. Now this one, you figured out pronto. You just knew as soon as I said what function has as its derivative 3x squared, almost all of you immediately said x cubed. So let's look at some more on page 284. Get there real quickly. And let's see if you can do the same thing with these problems that are in the exploration box on page 284. Part A, if I give you the derivative 2x, then what would be the function whose derivative is 2x? Just x squared. And if I wanted the whole family of antiderivatives, you'd say x squared plus a constant. And that plus a constant could stand for any constant. What function has as its derivative just x?
2? No.
1/2 x squared?
1/2 x squared. Because if I told you to differentiate 1/2 x squared, you would multiply the 2 times the 1/2. That would just give you the coefficient 1. Subtract 1 from the exponent, and that would give you the exponent 1. The great thing about integration is you can check it. It's just like when you learn to factor. You could always check your answer to a factoring problem. You can always check your answer to an integration problem by taking the derivative of your answer and make sure it gives you back what you started with. In the C part, what's the function whose derivative is x squared?
1/3 x cubed.
1/3 x cubed.
Beautiful. All right. Now, if that's just popping in your head, great. Or if you've already found how to find that answer, if it's not popping in your head, that's pretty cool too. This one's a little bit harder. What function would have as its derivative 1/x squared?
X to negative 3.
Okay, let's try. All right? That's the cool thing about integrating. We can check it. The D part said f prime of x equals 1/x squared. And I know I'm probably going to have to think of that as x to the negative 2. So let me check this answer. Is x to the negative is the derivative of x to the negative 3 x to the negative 2?
No.
to check that answer?
No.
Oh, it's not.
Negative 1/3 x to the negative 3.
We can check it. Negative 1/3 x to the negative 3.
That's not what I meant.
No?
No, that's not right.
Negative x to the negative first.
What about negative x to the negative first? I'm just checking anything y'all
Yeah, that'll be it.
yell out. To check your answer there, you would multiply the exponent times the coefficient. Negative 1 times negative 1 is positive 1. And then subtract from 1 from the exponent. And by golly, that does give you x to the next negative 2. So that's the antiderivative of x to the negative 2. Now, so what are we going to do as these problems get more difficult and God stops whispering the answer?
Hopefully there's a function or formula.
God's not even whispering these answers.
God stopped talking to Sarah a long time ago. Warren, how did you just know in a flash of light, or did you do something to figure out that negative x to the negative 1?
Well, I looked at it as x to the negative squared, and I'm thinking there's a coefficient of 1.
Yes.
But normally you would have a negative coefficient there if you have negative squared as the, if it's negative squared as the
Exponent.
Thank you, then you would have to have a negative out in front, which means in order to get the positive in the y prime, you would have to have a negative to begin with.
And you said if when I differentiate, I subtract 1 from the exponent,
You would be left with
then to anti-differentiate, I would probably have to add 1 to the exponent. Ooh, Warren just discovered a whole branch of calculus. Warren said, if I subtracted 1 from something and it gave me negative 2, what would that something have to be? Well, just add 1 to negative 2, and that's what the exponent would have had to have been. And to deal with the fact that when you differentiate x to the negative 1, you're going to have a negative out front. Then you're going to have to take the derivative of negative x to the negative 1 in order to get a positive x to the negative 2. Man, I hope that's written down as a rule somewhere, because I don't think I can talk myself through that whole process if I just have to figure out each problem separately. Miss Kayla?
Would that kind of make sense because you know how to, like, the opposite of plus is minus, the opposite of minus is plus. So, like, you know, the exponent is n minus 1. Would it be n plus 1?
Holy cow. Holy cow. There's my notes. We just about had an epiphany and I lost my notes. How does that happen? Epiphany. Dang it. I had them laying here just a minute ago. I know, but I had my copy right here.
You're just too excited.
I just got, gosh darn it. Did you see me writing on the notes? Am I crazy? Huh? No, I didn't flip it over. Lord have mercy.
Is it laying in front of you in that little piece of paper right there?
I put it under Elmo. There it is. Okay, play like that didn't happen and go back to what Kayla just said. Kayla said, if when you differentiate,
No problem.
are you with me?
With you.
Okay. If,
I got lost for a second.
well, I did too, apparently, but now we're all back together. Kayla said, if when you differentiate x to the n, you subtract 1 from the exponent and the exponent becomes n minus 1, then maybe when you anti-differentiate x to the n, the exponent should become n plus 1. Did I quote you correctly, Kayla? Then I'm going to change the name of this to Kayla's rule.
That's going to be boring. He helped me use that.
Kayla's rule, right there. Kayla's rule, part 2. To anti-differentiate x to the n, you have to do the opposite of what you do when you differentiate x to the n. You have to undo the differentiating. So instead of subtracting 1 from the exponent, you add 1 to the exponent. But also, when we differentiate x to the n, we bring the n out front. We have to, and multiply it by the x, we have to undo that. Instead of multiplying the exponent times the coefficient and then subtracting 1, we have to add 1 to the exponent and divide by that exponent. Let's see if that'll work in Warren's example. Warren just gave us the answer to the D part there. He said the antiderivative of x to the negative 2, if we added 1 to the exponent, we'd get negative 1. And then if we divided by that negative 1, well, dividing by negative 1 and multiplying by negative 1 is the same thing. So Kayla's rule worked on the problem that Warren just gave us. That's pretty cool. I think we're going to have to practice it some more to be convinced that it works, but it makes sense. If when you differentiate, you multiply, then subtract, to undo that, you would have to add, then divide.
What are you dividing?
By the new exponent.
So you just do the opposite of whatever you have to do.
That's exactly what we have done anytime we learn to do the inverse of some function.
I have a question.
Now yes sir.
So when the quotient rule comes up, do you
Holy cow, don't even think that yet. Don't even think that yet. Okay? Because by the time the quotient rule comes up, you're going to be in Cal 2, and I don't have to think about that ever again. Yeah, we're not going to undo the quotient rule in
But
Cal
would you
1.
divide and then multiply?
No, it's not going to quite be that simple.
Dang it.
All right, let's go back. See if there's anything else I need to show you in the book. From my notes, we have our new Kayla's rule right here. Yes, there are 2 other things I need to show you in the book, and then we'll do some examples from the homework. Page 285. If I ask you to, no, make this bigger. If I give you the function g of x equals x squared plus some constant, that is a whole family of antiderivatives. If I ask you what is the function whose derivative gives you 2x, you would say x squared plus any constant, and that x squared plus any constant would be the family of all derivatives. If I write, then the derivative of g of x is 2x, that's a differential equation. Now, most of you have to take differential equations, and we're going to deal with some today, but a differential equation is just an equation that involves derivatives. So that's a differential equation by virtue of the fact that this involves a derivative. This is g prime of x. In differential equations, you're going to take a derivative like g prime of x, and you're going to find the function whose derivative is that. You're going to anti-differentiate and have a whole semester of that. All right. Bottom of page 285, there's all the same vocabulary that I just typed on the handout. The symbol here is called the integral sign. What you're taking the antiderivative of is the integrand. Your dx is the symbol which tells you with respect to what variable you're anti-differentiating. F prime of x is some specific antiderivative of little f of x, but f prime of x plus c is the whole family of antiderivatives. All right, page 286. There are all all the integration formulas in the, well, not all of them. That's most of the differentiation formulas inside the front cover of the book. For every differentiation formula, you have an anti-differentiation formula called an integration formula. Here's the power rule for derivatives right here. The derivative of x to the n, you bring the n out front and then subtract 1 from the exponent. Same thing as an antiderivative rule. You add 1 to the exponent and then you divide by your new exponent. I'm going to cover this up for a second and see if y'all can help me figure it out. What function has as its derivative cosine x? Negative sine of x. Because if you just take the derivative of whoa. Yes, I got ahead of myself. The antiderivative of cosine is plain old sine, because if you take the derivative of sine, you do get cosine. What's the antiderivative of sine? Negative cosine, because if you take the derivative of positive cosine, it's not going to give you back sine. It's going to give you negative sine. So the antiderivative of sine is negative cosine. What about the, whoops?
So all the c's now are going to be positive instead of negative.
I'm going to think about that in just a second. What's the function whose derivative is secant squared? Tangent. What's the function whose derivative is secant tangent? What's the derivative, or what's the function whose derivative is cosecant squared? Negative cotangent. What's the function whose derivative is cosecant cotangent? Negative cosecant. So far, so good. What is the... in this iPad have a love-hate relationship. Yeah. What about the function whose derivative is e to the x? Just e to the x. Ooh. What about the function whose derivative is a to the x? First remind me.
A to the x times 80.
Yeah. I started to say, remind me how you differentiate a to the x. You get the same old a to the x, but then you have to multiply by the natural log of a. So to anti-differentiate, guess what you have to do?
Divide by the natural log a.
Divide by the natural log of a. The great thing is it's checkable. If your little spidey senses are going off and I'm not sure that's right, just check your answer, see if the derivative gives you back the integrand. All right, that's all of those we're going to talk about for a second. I'm going to show you the easiest examples in the book just to save us time writing, and then when we get to a little bit more difficult problems, we'll start writing them down. Example 2 on page 387. 287, yes. Example 2. I want the antiderivative of 3x dx, or I want to evaluate the indefinite integral. Those two things mean the same. I could say evaluate the indefinite integral of 3x dx, or I could say find the antiderivative of 3x. Well, just add 1 to the exponent of the x, and that gives you the new exponent 2. Then you have to divide by that exponent. Now, really, you can skip those 2 steps just fine. Add 1 to the exponent, and that will give you x squared. Divide by that new exponent, and you have 3/2 x squared. And then check your answer. The derivative of 3/2 x squared, you would multiply the 2 times 3/2. That would just leave you 3. Subtract 1 from the exponent, you'd have 3x. It checks, so that's the antiderivative. Just like when we were differentiating, very often we had to rewrite before we differentiated. we very often have to rewrite before we anti-differentiate. We have the original integral, we rewrite it so that we can use the power rule, we integrate it, and then we simplify our answer. And then we check our answer. There should be one more red box out there. If you give me 1 over x cubed, I'm going to rewrite it as x to the negative 3. Then I'm going to add 1 to the exponent. My new exponent would be what? Negative 2, and then I need to divide by that new exponent. The simplest way to write that is 1 over 2x squared plus a constant to get the whole family of antiderivatives. If you tell me to integrate square root of x, I'm going to write it as x to the 1/2. When you add 1 to the exponent, you'll get x to the 3/2, and then you have to divide by 3/2. But dividing by 3/2 is the same as multiplying by what? 2/3. So the simplest way to write the answer is 2/3 x to the 3/2 plus a constant. What about, if there's anything else I want to tell you. Oh, example 5 is a good one on the next page. If I don't think of a way I can rewrite example 5, I'm going to have to figure out how to undo the quotient rule, and I don't even want to go there. But in chapter, wherever we learn to differentiate, if you had told me to take the derivative of that expression, I wouldn't have used the quotient rule. I would have written that square root of x as x to the 1/2, and then I would have separated that into 2 fractions and simplified each fraction to avoid using the quotient rule. Well, the same thing when I'm integrating. I'm going to separate that into x over x to the 1/2 and 1 over x to the 1/2, and then rewrite both of those terms as simply as possible, and then add 1 to the exponent, divide by the exponent. Same thing in the second term. Negative 1/2 plus 1 is positive 1/2, and then divide by the 1/2. From now on, instead of writing divide by 3/2, I'm going to go ahead and say multiply by 2/3. And instead of saying divide by 1/2, I'm going to say multiply by 2, just to save ourselves a step there. And then there's the answer, factored as completely as possible. All right, let's jump in the book. 9 through 13. It's just like example 2, we're going to rewrite before we integrate. So I'm not even going to write these first ones down. Number 9, I'd rewrite that as what before I integrate? X to the 1/3. Number 10, how would you write that before you integrate?
4x to the negative squared.
1/4 x to the negative 2. You see why it's 1/4? 1/4 x to the negative 2. Number 11, I would write that square root of x as x to the 1/2. Then when I multiplied those x's, I'd have 1 over x to the 3/2. How would I write that before I integrated? X to the negative 3/2. What do you think I should do to number 12 before I integrate? Distribute the x, because I don't want to figure out how to undo the product rule. I want to write it so that it's not a product. Same thing with number 14. Just make sure that you remove the parentheses first and say that's 1 over 9x squared. And then how would you rewrite it before you integrate it? 1/9 x to the negative 2. Excellent. You got that.
I have a question.
Yes, ma'am.
What do you do with the dx? Can you like?
You don't do anything. I'm saying do in quotation marks. You don't do anything with the dx, but it has to be there to tell you with respect to what variable you're integrating. Look at That's a 10-point bonus word right there. Look at page 291. Your homework starts with number 5, so I just want to tell you something about number 6 and 8. Number 6, you're given the differential equation dr over d theta equals pi. Guess what the r would stand for? That's the radius, theta some angle. That's the change in the radius with respect to the angle theta is pi. And the directions say find the general solution of the differential equation. This is a differential equation because it involves a derivative. But now that we know that the dr really means something and the d theta really means something, we could multiply both sides by d theta and have dr equals pi d theta. And then just take the indefinite integral of both sides. When we integrate pi d theta, that's the integral sign. It looks like a capital S. Actually, it is the Greek letter capital S for sum, and we'll figure out why the word sum is associated with an integral, not today, but next time, whatever that is. When I integrate to find r, d theta tells me what my variable of integration is or what my variable of differentiation was. Instead of saying r must have been pi times x, this equation doesn't have x's in it, it has theta. R would have been pi times theta. And I could check that by taking the derivative of r with respect to theta. If I take the derivative of pi theta with respect to theta, what do I get? Just the pi that I started with. Now actually the direction said find the general solution to the differential equation. Don't forget your whole family of antiderivatives. R is pi theta plus any constant. That's the general solution. And then in later problems in the 70s somewhere, I'm going to give you the information to find that constant so that instead of the general solution, you can have a specific solution that satisfies that constant. All right? Yeah, that's something to look forward to. Number 8, here's my differential equation. dy over dx equals 2x to the negative 3. Well, if dy over dx equals 2x to the negative 3, then dy would be 2x to the negative 3 dx. Just multiply both sides by dx. And if the derivative of y equals this, then y, y would be the antiderivative of 2x to the negative 3 dx.
Oh, I thought that was an S you're doing. I
No,
guess
that's the integral sign.
Okay.
Oh, in piano, in music, yes. So what is y, or how would I find y? Using Kayla's rule?
Add 1 to the exponent.
That would give me x to the negative 2,
Now divide it.
and then divide by that new exponent. Add 1 to the exponent, divide by the new exponent. Don't forget your plus a constant for your general solution, your whole family of antiderivatives, and then if you can clean that up, you should. Of course you can clean that up. That's just negative 1 x to the negative 2 plus a constant.
Do you want us to keep the negative exponent or put it as a fraction?
I wasn't thinking of, hey, I should write that as negative 1 over x squared, but I probably should have been thinking that because the book never leaves negative exponents in the answer. So yeah, go ahead, in anticipation of what they'll have in the back of the book, go ahead and write that as negative 1 over x squared plus a constant.
So you're saying on a test we have to do these steps, we can't just do the shortcut?
No. Once you get the hang of it, you start skipping a lot of steps.
Just like doing derivatives.
Yeah, just like derivatives. You know, if I said take the derivative of 8x cubed, when we first did it, we brought the 3 out front, and then in the next step multiplied 3 by 8. We don't do that anymore. So you will absolutely be able to skip steps.
Okay, so you're just showing us how it works.
Exactly.
Alright.
Exactly. It's fixing to get way easier. What about, let's skip all the way down to 34. That d theta is just telling me my variable of integration. If I have a plain old constant, which I don't in number 34, but if one of these terms was just plus 5, then when I integrated it, what would it be?
0.
No, that's differentiated. If you differentiate 5, you just get 0, but if you anti-differentiate 5, you get 5x, only we're not dealing with x's here, we're dealing with theta. So if I had a constant term, when I anti-differentiated it, it would be 5 theta. That's why you need the theta to tell you what variable to put back on your constants. All right, so what's the antiderivative of theta squared?
3 theta cubed.
Add 1 to the exponent and divide by the exponent. Instead of writing divide by 3, I'm going to just save myself a step and say that's the same as multiply by 1/3. What function has as its derivative secant squared? Tangent. Then plus any constant, because any constant would not change the value of the derivative of that function. And I'm not going to write down all my checks, but I don't turn in a test on integration without checking my answers. 3 times 1/3 gives me just 1. Subtract 1 from that exponent and I'd have my theta squared back. And then the derivative of tangent is secant squared, and the derivative of a constant is 0. So that's right. What about number 40 has something sneaky. I just skipped all the easy ones because I know you can look at examples like the easy ones in the book. We looked at an example in the book where the numerator was a binomial and the denominator was a monomial, like x cubed minus x squared over square root of x. If I have a binomial over a monomial, I can just divide that up into 2 fractions and simplify each term. But that's not what I have here. Yeah, cosine over 1 minus cosine squared is not the same thing as cosine over 1 minus cosine over cosine squared. You can't take fractions apart that way because you wouldn't have a common denominator to put them back together. So, did you think of something else we could do?
Is that one of your,
Yeah, it should be sine squared.
1 minus cosine squared is just sine squared.
I forgot what it's called now. What is
Pythagorean identities. Well, I was excited, but now that I'm looking at it, I don't really see how that helps me.
Oh, you could make the sign into a negative.
Well, could you
It would
make it?
still be pretty.
I have to have that integrand being something that I recognize as a derivative of something else. The right-hand side of one of my derivative formulas. Miss Kayla?
Is there any way you can take like sine x into the second exponent, like to the exponent 2, and the derivative sign would be cosine? Negative cosine? No?
No.
Like 1 over sine squared x
Squared x.
multiplied by
I'm listening, Harriman.
Yeah.
1 over sine squared x, what?
times cosine x. No.
Okay, let's try it. 1 over sine squared x times cosine x. That is certainly a true statement.
But you still
I'm
have
not
to-
sure if it's helpful though, because if I can't differentiate factor by factor, I can't anti-differentiate factor by factor.
It wasn't 1 over sine squared, all the identities you gave us.
Okay, 1 over sine squared is,
Oh, it's
0.
1 over sine, isn't it?
well, 1 over sine squared is cosecant squared, but cosecant squared cosine is still not one of my derivative formulas I have memorized. I'm going to give you a hint here. It's some other way to break this up other than this. This
Does that
was
have to do-
legal.
Yeah.
Does that have to do with tangent
Yeah.
Maybe.
times the 1 over sine squared?
Maybe. Cool. I think several of you figured it out at the same time. This wasn't a bad thing to try. I mean, sometimes you just have to write something down and look at it and go, well, that's true, but was it helpful? And that was true, but no, it wasn't helpful. So mark it out and try something else. What about writing that cosine over sine squared as 1 over sine times cosine over sine? First, see if it's true, and then we'll see if it's helpful. Does that multiply back together to give us what we started with?
Yes.
Yeah, it's true. Now, is it helpful? How is that helpful?
Because you know what the derivative of one
Cosine over sine.
No, cosine over sine is cotangent. 1 over sine is
Negative.
cosecant. Cosecant x cotangent x.
That's the derivative of cosecant.
Very close. If I say that answer is cosecant,
oh, it's negative.
yeah, if I just say the derivative is or the answer is cosecant, then when I take the derivative, I'd get negative cosecant cotangent. I don't want negative cosecant cotangent because that's not what I started with. So I just need a coefficient of -1.
Those are going to be on the test.
It was all in figuring out how to rewrite this original integrand. And as always, as long as we're dealing with polynomials, algebraic functions, those are easy. When you get into trigonometric functions, it's going to take some more work.
So you rewrite it to where it's in the formula that you memorized?
You rewrite the integrand as one of the formulas that you have memorized. In 5.1, all of the integrands can be rewritten as formulas you have memorized. In Calculus 2, you have to say, well, what if I can't write it as something I have memorized? There's something called integration by parts, and that's the only word I remember from Calculus 2. I blocked the rest of it out. All right. What about 42?
I really said that.
What function has as its derivative cosine x? Sign or negative sign? Just sign. Just sign. All you have to do if you're not sure is check it. Ask yourself, if I take the derivative of sine, do I just get cosine? And the answer is yes. I mean, if you accidentally write down a minus, as long as you're writing in pencil, you just erase it. What function has as its derivative 3 to the x?
Same ugly times the divided by the.
It would definitely have to have a 3 to the x, but if I think that that's all there is to the answer, let me think how I would check it. Let's say that I think that's my answer with plus a constant on the end. If I go to check it, then the derivative of sine x is cosine x. So far, so good. But the derivative of 3 to the x is not only 3 to the x, it's also what?
Natural log.
Of the x.
Multiplied by natural log of 3. Now, Kayla, you could say, and the derivative of x, but the derivative of x is just 1. I'm going to make you a note out here just in case you've forgotten. The derivative of a to the x is a to the x times the natural log of a. When you differentiate a to the x, you have to multiply by the natural log of a. So when you anti-differentiate 3 to the x, what are you going to have to do? Divide by the natural log of 3. You could either put that 3 to the x over natural log of 3, or you could say the whole thing's multiplied by 1 over natural log of 3. But if you have any doubt in your mind about whether that answer is right, then take the derivative of your answer and see if it gives you back the original integrand. Yes, the derivative of sine is cosine. 1 over natural log of 3 is just a constant. I don't know exactly what it is, but it's just a constant, and I can keep up with it while I'm differentiating 3 to the x. The derivative of 3 to the x is 3 to the x natural log of 3. And the derivative of that constant is 0. So is that equivalent to my original integrand?
Yes.
Sure it is, because that 1 over natural log of 3 times natural log of 3 cancel each other, and there's your original integrand.
And so, like, do you just put, like, okay, you get your answer after the interval sign, do you just put equals?
Yes, yes. That was a good point, Ashley. The antiderivative of this equals that. The antiderivative of this equals that. All right. One more of these. What about, I'm just going to make this one up. Or actually, I know where there is one. Nope, I'm going to make it up. Antiderivative of x to the negative 1 dx equals what?
One over x.
I could check that, but I don't think the derivative of 1 over x is negative 1 over x squared. That wouldn't be right.
Undefined? Is it undefined?
It's just saying.
X is 0, ain't it?
1, wouldn't it?
Y'all are realizing that there is a problem. Because if I add 1 to that exponent, I get x to the 0. That's not a problem. X to the 0 is not a problem. But then I have to divide by that 0, And that's where the problem comes in. I can add 1 to the exponent, but I can't divide by 0. Our power rule's not working so well right here, is it? What if I wrote that x to the negative 1 as 1 over x? Is that the same thing?
That's what I was trying to.
Yeah, that's definitely the same thing, but it's easier for me to think of a function whose derivative is 1 over x. What is it that if I took its derivative, I got 1 over x?
That's all it is.
Oh my goodness.
That's what I was saying.
Oh.
Nice.
Pretty darn cool. So if we look back at Kayla's rule on the handout, there was actually a part of Kayla's rule that Kayla didn't even realize was there yet. The power rule for integrating says for any real number except n is negative 1, for any exponent except negative 1, you can just add 1 to the exponent and divide by the exponent. But when n equals negative 1, you have x to the negative 1. That's 1 over x, and the antiderivative of 1 over x is natural log of x. So you can't use the power rule on x to the negative 1. That's the only exponent that the power rule doesn't apply to. Miss Kayla?
So if you had 3x to negative 1 will be 3x.
Yes. 3x to the negative 1 or 3 over x would be 3 natural log of x. All right. Checking something else real quickly. I think I know the answer, but I'm just double checking. Nope, never mind. Yep, do mind. There it is. The formula for the antiderivative of 1 over x in the book, the antiderivative, focus, the antiderivative of 1 over x dx is natural log of absolute value of x. We've seen that absolute value before and said it doesn't affect the derivative, it just affects the numbers that you can use for the argument. If you have natural log of absolute value of x, then x could be positive numbers or negative numbers. And the derivative would still be 1 over x. I'm telling you, I'm not going to count off for this on the test. But if you want it to be perfectly correct, when you anti-differentiate 1 over x, it's not just natural log of x, it's natural log of absolute value of x. So I want to go back to what I just wrote on my paper here and make sure I've written that correctly. Not just natural log of x, but natural log of absolute value of x. All right, we have about 15 more minutes, 10 or 15. Let's skip over to the problems 63 to 72 that say solve the differential equation. This is just baby DE. That's where we are right now. And most of you have to take differential equations. This is your first taste of it. I'm sorry, what?
Where are you?
63 to 72. On page 292. Yeah, same page, just skip over to, let's say, number 66. Actually, 5 through 8 had said find the general solution of the differential equation, and that's why our answers had that plus a constant. That was the whole family of solutions or the whole family of antiderivatives. In number 63 to 72, it just says solve the differential equation. So it gives us the information that we need in order to find out what that constant is. On number 66, not only are we given the differential equation f prime of s equals 10s minus 12s cubed. That's a differential equation because we're given an equation involving a derivative, but we're also told that f of 3 equals 2. Now we'll figure out what to do with that f of 3 equals 2 in just a minute. But I'm looking for the function whose derivative is 10s minus 12s cubed. And to find that function, I would just evaluate the indefinite integral of 10s minus 12s cubed with respect to s. I'm given the derivative, then the original function is the indefinite integral of f prime of s. And what is that antiderivative? What's the first term? 5s squared. You added 1 to the exponent, and then you divided 10 by your new exponent. 10 divided by 2 is 5. And sure enough, if you differentiate 5s squared, you get 10s. What is the antiderivative of 12s cubed?
3s to the fourth.
You added 1 to the exponent, and then you divided 12 by that new exponent and got 3. And then you could check it. 4 times negative 3 is negative 12. Subtract 1 from the exponent, you get back your s cubed. So that is f of s, but f of s could also have plus any constant on the end. This is the general solution to that differential equation. But in number 66, we don't want the general solution. We want the exact solution. The one solution that not only has the derivative 10s minus 12s cubed, but also satisfies f of 3 equals 2. What does f of 3 equals 2 tell us?
The x is 3 and the y is 2? Or the
If we replace all the s's with 3, then the value of that function is 2. In other words, we can put 2 in the place of f of s, and 3 in place of all the s's, and solve for that constant.
So it's negative 38.
You're just a little bit ahead of me. I think you're probably right.
I think.
3 to the fourth is 81 times 3 is 243. So far, so good? Whoops, you can't see.
Yes.
Is that what you said?
No, I did it wrong.
Does anybody second my answer? And feel free to disagree if I've made a mistake. I think I've done it correctly.
That's what I got.
Okay. I don't know who that was or what your class average is, but I'm going to trust you. If you agree with me, then you and I are right. All right, so our specific solution, I barely have room to write it here. Our specific solution, I can't spell specific, specific. There we go. Our specific solution is f of s equals not just 5s squared minus 3s to the fourth, but 5s squared minus 3s to the fourth plus 200. That is the only function in the whole wide world that satisfies both of those conditions. Its derivative is 10s minus 12s cubed, and you can double check. If you put 3 in the place of s, you should get 2 for your y. So that's baby DE. DE first day. All right, let's do one that has trig in it, and then I really wanted to have time to do one word problem. We shall see if that happens or not. Oh my goodness, look at number 70. I'm so excited. And just remember why I'm a math major.
Double derivative.
They give us a second derivative. Holy cow.
You gotta only find the first derivative. We gotta find we gotta do it twice.
Yep. On number 70, it's a differential equation, but we're given a second derivative. How would we find the function which would be the first derivative?
Take the antiderivative.
Ooh, y'all are good, using good words. Anti-differentiate sine x dx. And what is the antiderivative of sine x dx? Just double check. If you think it's just cosine x, then when you check your answer, you'd get back a negative sine x, and that's not what you want. So it must be negative cosine x plus some constant. That's the whole family of antiderivatives.
You can set that equal to 0 and find C.
Well, I need to use this information from the first derivative to find that constant before I anti-differentiate again. I'm going to say since f prime of 0 is 1, what does that tell me I can do? Let x be 0 and set the whole thing equal to 1. 1 equals negative cosine 0 plus a constant. What's cosine 0? 1, and then the opposite of that would be negative 1. So our constant is 2. And so the specific first derivative, not the general anymore, is negative cosine x plus 2. If you take the derivative of that, do you just get sine x? No, if you take the derivative of negative cosine x, yes, you just get back this sine x. So far, so good. But now we don't want just the first derivative, we want the original function. So f of x would be the antiderivative of negative cosine x plus 2 with respect to x. What function would have as its derivative negative cosine? Negative sine. What function would have as its derivative just 2? 2x. And then the whole family of antiderivatives, f of c. Or not f of c, just plus c is what I meant to say. That's a general solution, but we want the specific solution. And to get the specific solution, we need to say, since f of 0 equals 6, I can just let x be 0 and solve for that constant. What's sine of 0? 0, and 2 times 0 is 0, and 0 plus c is c.
Yeah.
So that constant is 6. And our specific solution to that differential equation is negative sine x plus 2x plus 6.
Can we do it? Never mind.
Pretty darn cool. All right. That's all you do, 63 through 70. Maybe I have time to sneak this one word problem in. I do want today's homework. Today's homework is 4.8. Was it the whole thing? Because we did 4.8 in just one day. Yeah. Yes. Harriman, either y'all get together, turn in the homework in one envelope, or y'all march it down individually to the math science office, whichever you prefer. And Miss Sonia was supposed to put your last homework in the mailbox. So y'all should have homework in the mailbox returned, and then you send me today's homework. Tonight's homework is on the notes, and you should definitely be able to do 5 through 43 and 65 to 72. These are just odds, so ignore the 72. Let me see what 77 is. And I'm afraid I'm not going to get to talk about that. I'm going to say just stop right here. Try 77, but don't worry about those last 3. Yeah, unless you get it, and then just keep going with your wonderful self. I would start number 78, but I know that Miss Idea lady would tell me that she's going to turn me off in 2 minutes, so I'm not even going to start. Just let me say this. If I give you the position function, what does the first derivative give you? The first derivative gives you velocity, and the second derivative gives you what? Acceleration. So if I give you an acceleration function and you anti-differentiate it once, what's that going to give you? Velocity. And if you anti-differentiate it again, it's going to give you
Position.
the position function. So you just converted the word problem to a problem just like number 70. You're given acceleration, which is a second derivative. You have to anti-differentiate twice to get back to the original position function.